end, error correction will be needed to execute complex algorithms in quantum computers. And even if the error correction techniques that we will use in the future for fault-tolerant computers are not the optimal, are different from the near-term error correction techniques that we have now, it's still interesting to run the actual error correction code in the devices that we have now to learn things from the experiment and not just developing new theory codes without actually knowing how the code performs on the real device. And since we had access to IBM devices, thanks to the IBM Quantum Credits program and our collaboration with the University of South California, then we decided that it would be a quite good project to try to implement the surface code on those devices. In the end, all the devices that we have now, if they want to become a fault-tolerant quantum computer, they will have to show a key milestone, which is a scalable QEC advantage, which means that if we increase the number of physical qubits, we can arbitrarily reduce the logical error rates. This is something that was recently achieved by Google's devices the last year. But in the end, as I said, all other architectures will also need to show this milestone. And this is what we are trying to achieve. And in order to do this, we need a number of physical qubits in the devices, which ranges in the order of hundreds or thousands of physical qubits. We choose the surface code, which is the planar version of the QTYR story code, because it's really simple and has a good performance, which means that it's interesting for near-term devices. This is a stabilizer code, which means that we have many physical qubits to encode, in this case, a single logical qubit. And the extra redundancy provided by the physical qubits is used to create a set of operators, which are called stabilizers, which are many-body operators that we can measure. And if an error happens, these operators will be flipped. And depending on the measurement outcomes of these stabilizers, we can apply a correction so that no logical error happens. So for example, in the surface code, we have wait-for operators, which are the code stabilizers, and we have C-type stabilizers, which are depicted in blue, which correct and detect and correct bit flip errors, and then we have X-type stabilizers, which detect and correct phase flip errors. And once we are able to correct both bit flips and phase flips, then we can correct any arbitrary single qubit error. An important result for error correction is the threshold theorem that says that provided that the physical error rate of each of the individual qubits in the device is below a threshold error rate, then by increasing the lattice size, in the case of the surface code, in the end, the number of physical qubits, then we can make the logical error rates to be exponentially suppressed with respect to the lattice size, which in this case is also the code distance. So for a d times d square lattice, we have d, which is the code distance, which is ultimately related to the number of errors that the code can detect and correct. But we can also consider non-squares or rectangular lattices, for which we increase the code size in one direction or in the other to increase the protection against a particular type of errors, either phase flips or bit flips. Another key problem in error correction is that we have to measure these stabilizers, which are many-body operators, but measuring a many-body operator is not a native operation in the typical quantum computers that we have now. So instead, we have to find a circuit that implements this many-body measurement. And it is critical that this circuit is fault-tolerant in the sense that if an error happens at any place in the circuit, then it doesn't propagate to other physical qubits as that would spoil the fault tolerance of the circuit. So for example, the traditional way to do it for the surface code is by using an extra ancilla qubit. For example, this is to measure a C-type stabilizer, which requires a square grid connectivity. This is what Google had in their superconducting devices, but which is the reason for which they have those really good results with respect to the surface code. But IBM doesn't have a square grid connectivity, but rather a heavy hex connectivity. So we cannot implement this version of the surface code. There's an alternative single instruction circuit proposed by Matthew McEwen and collaborators, which instead of using an ancilla qubit, it maps the stabilizer to as one of the qubits in its support, and it measures it. By using this circuit, the connectivity is reduced to a hexagonal grid, but it's still not the heavy hex grid that we need. So what we did in this recent work was to implement the surface code on the heavy hex lattice by taking the original different identities, and for example, we apply here a swap gate so that we have the data qubits in the vertices, and then we have some bridge qubits in the edges of the heavy hex lattice. And when we combine both identities, we get this kind of circuit, which implements the single instruction for the surface code on IBM devices. What we see here is that the qubit overhead, of course, is increased, and due to the increased number of gates, the threshold is impacted, but nevertheless, this is one of the best scalable error correction codes that can be implemented on the heavy hex lattice. We also had some other troubles when implementing the code on the heavy hex lattice, and IBM devices in particular. First one is that quantum error correction requires a supply of fresh ancillas for single instruction, but IBM devices do not implement unconditional reset operators, which means that in principle we cannot reuse ancillas. We solved that by tracking resets by software. So whenever we measure an ancilla qubit, then after that we consider that qubit for the next round to be in the same state as the one that we previously measured. And by doing so, we reduce a little bit the overhead, and the performance is increased a bit. And also a thing that we see here is that in comparison with the traditional surface code, there are many free gaps here or here, for example, where we can insert dynamical decoupling pulses to further improve the performance. So for example, in this long gap here, we can insert a long and robust dynamical decoupling sequence. And in this short gap, we can insert a simpler sequence. And we have seen that this provides a performance boost. And next critical step for error correction is to define a noise model. The noise model is interesting, of course, for simulations to predict what would be the performance of the device in the real device, but it is also required for decoding. Recall that we have a list of stabilizer operators that we measure, and then we have a decoder that has to take the information from the measurement outcomes and convert that to bit or phase flips applied on the physical qubits to correct them. For this decoding to work, we also need a noise model that helps the decoder to interpret those measurement outcomes. Both the simulations, which use a lot of qubits, and the decoding require that our noise model is restricted to Pauli operations. So the noise model that we consider is circuit level noise, in which after each ideal gate in the circuit, we apply a bit flip or depolarizing channel, depending on the gate. And also we apply idle errors on idle qubits with a probability which is proportional to the time during which the qubit is idle, and with a bias that is phase flips are more dominant than bit flips, which depends on the coherence times. And we use different sets of error rates and times for each of the qubit, and this data so individually for each qubit, which are obtained using randomized benchmarking and provided by the IBM platform. So with this, we have all the ingredients, and we can now run the code on the real device. This is result in one of the latest available IBM quantum devices. And I'm plotting here the performance of a lattice size of 3 × 3, which is the blue line, and also 2 rectangular lattice sizes of 5 × 3 and 3 × 5, each of which increases the performance for bit flips or phase flips separately. And what we see is that we are below threshold for those situations. So if we focus on bit flips, then the performance of the green line, which has an increased protection against bit flips, increases the fidelity, which means that the code is below threshold for bit flips, and something similar happens also for phase flips. Unfortunately, we cannot increase the protection for and reach a 5 × 5 code because that doesn't fit in the IBM device. So instead, we can only simulate that because we don't have enough number of physical qubits. But still, we see that the simulations predict that the result is quite close to break-even. Another thing that we see is that dynamical decoupling has a great effect against phase flip errors, improving the performance of those codes. So now to finish, we have seen that the surface code can be embedded on IBM devices, and we obtain a below threshold situation both against bit flips and phase flips separately, but not simultaneously because we cannot implement that code yet. We also saw that dynamical decoupling is interesting as it increases the performance, especially against dephasing errors, even though there are some situations where we cannot apply DD. And also, we saw that performance predict the performance of the full code, which of lattice size 5 × 5 to be really close to break even. So that's all. Thank you for your attention.
Thank you so much, Cesar. Do we have any question? Okay, so I was wondering if these kind of error correcting codes could also protect against errors in several qubits at once, not just one qubit, like a bit flip and so on.
In principle, with this code, you can only correct qubits affecting one qubit. But if you increase the code size, then you can also correct errors affecting 2 qubits. But if there's like a correlated error that affects both qubits at once, then you cannot correct any further qubits. So if you have a single event that affects 2 qubits, that counts as 2 errors and not as one. Okay. So in that sense, these error correction codes cannot take into account correlations.
Okay. Thank you. Any question? Okay, sure.
Just before, you considered that you only had dephasing on your CNOT gate, or did you assume a more specific model? And are you also going to, no, depolarizing, yes, sorry. Are you also going in the future to, because these CNOT gates are probably also biased, and you don't have as much bit flip error as dephasing errors? And are you going, for example, to use some quantum process tomography to start having a, how to say, a more specific model of noise of this CNOT, for example?
We have some insights on the CNOT effectively being biased. Yeah, that's something that we definitely could look in the future. But I don't know how much would it affect the decoding part of the, so because it definitely will affect the accuracy of the simulations. But for decoding, you have more freedom on how you define the noise model.
Okay, so let's thank the speaker again.
Sí. ¿Están descargadas?
Sí.
Ah, vale, la botan.
Pantalla completa. ¿Esto cómo se hacía?
Y,
Aquí, vale.
Ah,
Este
cacho.
es puntero láser,
y esto...
pasar
vale.
y anterior.
Vale, a ver, voy a... Vale.
Sí, ¿no? Perfecto.
Uso este micrófono mejor, ¿no? Que el otro.
Sí, habla con este. No, pues simplemente hablas.
Ah, vale.
Okay, now let's listen to the talk by Roberto Ruiz, which is titled The Beth Ansatz, Quantum Circuits, and the F-Bases.
Well, thank you, and thank the organizers for the opportunity of delivering this talk here today. Well, this talk is based on a paper that has been recently published, and in fact it's part of a larger scheme or program that has been developed around the IFT during the last years. So it's concerned mostly with the adaptation of integrable models to quantum circuits. Since one is involved with integrable models, let me review briefly the former, or so, yeah. What's an integrable model? Well, an integrable model is a quantum many-body system in one dimension that exhibits or features a maximal, virtually infinite number of commuting conserved charges that are often required to be local. And this property often leads, but not always, to exact solvability in that we can find the spectrum, the eigenstates, some correlators analytically. It also affects the dynamics. For instance, normally every scattering event must be decomposed or factorized into sequences of two-body events, each of which conserve the momenta involved individually. So only transmission and reflection is allowed. And yeah, the Bethe ansatz is nothing but a method to construct the eigenstates of these models as long as the number of particles or excitations is conserved. In this case, we will say that the particles are the number of spins down, here depicted. And well, in its first formulation by Bethe in 1931, it consisted of trial functions. One is, Bethe tried to diagonalize the Heisenberg model in one dimension. He considered linear superpositions of plane waves whose coefficients are the S matrices I introduced before. So yeah, one will have this kind of linear superposition here. And in fact, this approach can be systematized in creation-like operators acting on a reference state. One may think about the harmonic oscillator when one has actual creation operators on the vacuum. And this sequence of operators are based in the R matrix. The R matrix is a 4x4 matrix for this model that allows one to frame this linear superposition of plane waves as a network, a tensor network. Below we encounter the quantum space, as is often known in integral models. We also have some auxiliary space with specific boundary conditions so that each row corresponds to a V operator. Here we will have 4, for instance. And yeah, and the output will be the state we are looking at, or we want to. So each of these parameters that are implicitly involved in the network, for the states to be eigenstates of the XXX Hamiltonian, they should satisfy a set of equations that go by the name of beta equations. And yeah, that's pretty much all. In fact, the linear superpositions of plane waves can be directly framed as a network of this sort that goes by the name of matrix product state as well. But yeah, so that's more or less all I wanted to say about integral models. And the problem we are interested in is trying to frame this sequence of creation-like operators acting on the reference state, which are non-unitary in general, as a sequence of unitary operations acting on another reference state. Well, there has been some work with different approaches, and well, we'll focus on those papers for, yeah. And well, we will want to do that. Well, I'm giving some motivation here, is that as mentioned in the first slide, we have access to some properties due to exact solvability and in particular correlators. If we were to measure some, say, two-point function of two Pauli matrices, we will be addressing a quantity that we know how to compute analytically. And if we perform the measurements in a classical device prepared in a beta states, we could compare the results and somehow certify what's the performance. This is rather vague, don't take it too seriously. But yeah, it will be one idea. Another idea is like for those correlators that cannot be computed with a classical device anymore, one will be exploring a kind of realm of quantum advantage. And another sort of like applications will be like one could, if one had prepared these beta states in a classical device, one could later run real-time evolution algorithms that normally cannot be simulated with tensor networks, or one could address the adiabatic preparations of ground states for those integrable models that are connected to other non-integrable interesting models, etc. This is a bit of motivation for the problem. And yeah, what we did in particular is using some structure or intricacies, the specifics of the beta ansatz, not every state, but just those states in principle, to turn the sequence of operators as like these P operators here that are unitary, acting on this reference state. Well, the diagrammatic representation, sorry, will be this one. One will has this initialization. One has these P unitaries. And when ends up with the beta state, there are no post selected qubits, so the circuit is deterministic. And the point of this approach is that we know the P's exactly. We know the analytical expressions of these P's, even though they act on more than 1 or 2 qubits. So we know them analytically. We can prove by virtue of some of the properties of the networks I showed before that those are exactly analytical. We could get rid of the auxiliary qubits that appear in the tensor network reversely due to properties of integral models. And for the time being, we have an approach that applies to the XXZ model with for every anisotropy. This is important for later consideration, but yeah, let us take this model as the one that has this form, although we also provided a framework to approach other integrable models. And the picture we ended up with is this one. Normally one starts from the systematic point of view, so the algebraic beta ansatz, the green one. And in the first work by my collaborators, they perform some numerical techniques to arrive to this piece and numerically. In the second work, we frame the linear superposition of plane waves as a tensor network of this sort, and we use some of the properties, namely exchange or exchange symmetry of these tensors and under like swapping of qubits, and then we arrive to this piece analytically. And in the last paper, we use the F basis to provide a general framework to start from here, which is the normal, the standard starting point, to arrive here to the exact unitaries. So that's more or less all. There's MPS in the center, in that this tensor network are really at the core of all the construction. And yeah, this is more or less the summary of what I said just now. What are the problems? We don't know the efficiency. We know that the number of unitaries should be like linear in n, so the number of qubits. But each of these p's act on n+1 in general, but for this one, that's quite technical and not very important. And we would like to know how these p's decompose in terms of 1 and 2 qubit gates. If one addresses an brute force approach, one finds that these p's are exponential in m, so exponential resources. But for instance, for the delta equals 0, which corresponds to a non-interacting point, we know that this piece, or rather a gauge choice of this piece, could lead to a polynomial number. In fact, linear number of 2 qubit gates, match gates. Yeah, so a polynomial number of gates in general. Right now we are exploring how to decompose this piece in general for delta different from 0, but that's perhaps too early to say something for sure. There are some preliminary results, but still unclear. Also, since one should solve a set of equations for those outputs that are like eigenstates, actual eigenstates of the Hamiltonian, one should take into account that the beta equation should be solved, and that adds another layer of complexity. And another approach is to address other models, because, perhaps this XZ model is too complicated for whatever reason, and one would want to address other models in this framework of the F basis to check whether there exist efficient circuits in terms of the number of 1 and 2 qubit gates involved. And yeah, that's one approach, and yeah, one may want to look at the F basis for these other models. And that's, I think, pretty much all I wanted to say. Thank you.
Do we have any question?
Hi, thank you very much for your presentation. As I understand it, you're studying mainly Heisenberg, Hamiltonians, and this sort of integral system. These models can exhibit quantum criticality, like long-range correlations in certain phases. Do you have any idea what sort of effect that could have on the efficiency of preparing your states?
Actually, we found, and there is no, so if we try for the gap phase for delta greater than 1, or delta equal 1, or we try different deltas, and it seems it does not really affect the way in which these states are prepared. Also, one should take into account that this circuit prepares offset states, meaning that they are not they do not correspond necessarily to eigenstates, so that's not reflected there. But what is reflected is the Jack-Buster structure. If you are a bit familiar with that, this type of constraints are reflected, but those regarding the thermodynamical properties of the unitaries not. What I can say is that the problem you are talking about may be reflected in another approach, but recent approach by these people here, because they use the thermodynamic Bethe ansatz to construct efficient circuits, approximate circuits, and I believe that in that case, or I expect that in that case, some differences could appear. So yeah, that's.
Thank you very much.
Do we have any other question? If not, I would like to ask, continuing the previous question, whether the limitation of this kind of models with phase transition and so on could manifest in the construction of the MPS states, because in that case, I mean, I understand that you cannot really represent all kind of states with critical points and so on.
Yeah, well, so your question is whether one point. First, for the XXZ model, Fadegen and Takhtajan proved that all the eigenstates of the spectrum could be constructed with the Bethe ansatz. So I could express every state of the Hilbert space as a linear superposition. And you are asking, well, whether this would imply that there exists an efficient MPS representation for every single state. I will say that no, and this is reflected in the fact that here in this picture, for say a half filling level, we will have like a bond dimension of 2 to the n over 2. Yeah. So the MPS will not be efficient. I'm not sure. I'm not sure how is the circuit affected in that way, because we don't know the efficiency of this decomposition. Definitely, we will have larger gates because those act on m, and for m equals n over 2, for instance, we will have that they are larger. So the factorization should involve a larger number of gates, but right now, I don't see why it should spoil polynomiality of the compilation of the unitaries in case it exists. So, yeah, that's my answer.
Thank you. Okay, so let's thank the speaker again. Okay, so let us now listen to a talk by Marc Carrillo, titled Hybrid Classical Quantum Approach for AC Optimal Power Flows.
Okay, well, thank you very much for the organizers for inviting me here, also for all of you for attending, and my colleagues, Sara, Monica, Sergio, and Antonio, that helped me with my master thesis. Okay, I must say that we are all engineers, so we don't know that much about quantum computing, but we are trying to make applications on real world, on real world, using quantum computing. Okay, in real problems in electrical engineering. Okay. First of all, I will explain the electrical problem that we are dealing with, which is AC optimal power flow and how it classically solved. Then a brief explanation of quantum adiabatic evolution, how we merge these both classical and quantum computing for solving the AC optimal power flow, a case study, simple case study, the results obtained, and finally a conclusions and some lines of future work. Okay. Okay. Optimal power flow is a fundamental optimization problem in power systems. Okay, aiming to minimize the generation cost dispatch while satisfying some operational and technical constraints. Not only is crucial for day-to-day operation of the network, but also for the planning in order to correctly place all the resources that we have on the network, such as generators, batteries, everything. Okay, the classical formulation of these problems, okay, is minimizing a cost function based on the power injections of active and reactive power, okay, and subjected to some operational constraints, as I said before. This problem can be solved in DC networks and AC networks. In this case study, we are dealing with an AC transmission network, okay? Some concepts that are important in AC networks are the difference of powers. Okay, we have the active power, which is the usable power, the reactive power that is not usable, but is necessary for inductive and capacitance loads, and the apparent power. Okay, I'm sure that if any one of you have done some classes on electrical engineering or electrical systems, the teacher used this example, okay, this analogy of the beer, which is the active power, and the foam is the reactive power. Okay, it's just a representation that is commonly used. Back to the presentation. Okay, there are many classical solvers that can deal with this problem. Okay, but one that we are using is the interface of Panda Power. Okay, that solves the optimal power flow using the internal point solver. Okay, where the starting point of the optimization is the center of the operative constraints. I mean, if one generator can give between 10 megawatts or 350, it will use the center point, okay? Panda Power not only helps us solving this by giving us the power injections of active and reactive power, it also gives us the voltage magnitudes and angles of all the buses, okay? And helps us model the network, changing some parameters. This is important for this study, okay? Changing some parameters of these components. So, for quantum adiabatic evolution, okay, this is the quantum method that we are trying to introduce here. The idea of quantum adiabatic evolution is slowly evolve a quantum system from easy to prepare ground state of a simple Hamiltonian into another ground state of a more complex Hamiltonian that encodes the solution to our problem, okay? The library that we are using is Kibo, okay, with the KiboJIT backend. In order to do this. I will not explain that much because I know that you know probably much more than me. The thing is, why the addition of quantum computing in the solution of the AC optimal power flow? Well, see, the problem that we are dealing with is that this optimization problem is super complex. Okay, we have networks that are huge with 300,000 of buses, and also the constraints are nonlinear and complex. So some classical solvers struggle or directly not converge finding the solution. So what we want to do here is, by using quantum adiabatic evolution, give the operational topology of the network with activation and deactivation of some of the parameters of the network. With this, we can reduce the complexity and find the solution, okay? Okay. The main idea of this study is to find a 24-hour optimal power flow in AC transmission network, okay? What does this mean? This means that this algorithm is a prediction of the operational cost in a range of 24 hours in the future, okay? We have to split the problem into a subproblem, which is the classical formulation of optimal power flow, the 24-hour load profiles, some cost generations, and finally the modeling of the network, okay? Then the other problem, which is totally correlated with this classical optimal power flow, is a binary integral linear programming model, okay? The advantage of this is that we have to create a new model, okay, with a binary set of activation and deactivation of the components. So this will be translated into our Hamiltonian with some previous transformations to Kubo and Ising, and this Hamiltonian will be passed through adiabatic quantum evolution. So, sorry. So this combination of activation and deactivation of some parameters will be set into Panda Power network. As I said before, you can change some of the parameters. So this network now, the operational topology is put into the network, and the classical solver will try to find a solution. If the classical solver converges, we have found a technical and cheaper optimal solution. But if not, the combination found in the adiabatic evolution process has to be introduced again as a penalized constraint into our model. So the next time, then in the next iteration, will be not feasible, okay? So this is the main idea for this hybrid approach. Okay, the case study, this is the case study that EEEE 9-bus system. You can find documentation in Panda Power and a lot of different sites in internet, okay? It's a transmission line, it's a very small transmission line. And we have, you can see that we have 3 loads connected to it, which is the demand of the network. Here are the profiles forecasted with machine learning, okay? For the active power and the reactive power, this is the demand that in every hour we have to supply, okay? Another thing that we have is the external grid, that it must be active, okay? It must be active because it's connected to a Slack bus, but it's some technical stuff that I will not explain. But it has to be active. So the only things that we have touched here is the generator 0 and generator 1, okay? So for these two generators, we have to create 3 binary variables in order to do the quantum adiabatic evolution. U tells us if the generator is active in this hour, B tells us if it's activated in this hour, and W if it's deactivated in this hour, okay? So we must add also a constraint here that relates all these states for this hour and the previous one, just in order to make it work correctly and with sense. And the objective function that you can see here, okay, of the optimization problem is the sum of the generators, the active variable for the cost of the injections of power of active and reactive power, and also the cost of the startup and shutdown of the generators. Okay, these costs, okay, you can see here for the injections of active and reactive power, it depends on the power that you inject with these parabola functions. And startup and shutdown costs are fixed due to the complexity of activation and deactivation of the generator, okay? This is technical stuff and the RAMs and how do you model it. So once we have done this hybrid approach, we can see some results here. I have a lot more, but I didn't want to put that much. Here you can see the evolution of the operational cost for every hour. This is a prediction, of course, because the loads are predicted, but it's a probabilistic optimal power flow. And you can see how the evolution works. Also, you can see here the results of the quantum process of all the states of the binary variables. For example, you can see that in hour 0, the generator 0 is activated. It's active for 4 hours, then it's deactivated. Well, you can see all the evolution here. And finally, you can see the active and reactive power injections for every hour. So these are the main results that we have here connected to the quantum part. Okay. Well, to conclude a little bit, the model shows good results with reliability. As I said before, we are engineers, so we are trying to focus on the part of the application of all the algorithms of quantum computing in real-world cases. And we will like to test some more complicated networks, such as, for example, a distribution part that is more complex than transmission sometimes. And, well, add more binary variables. We have another problem that it's optimal transmission switching, that you can also play with the activation of lines instead of the generators only. So there's a lot of them. And finally, this was, we presented this into Spanish Supercomputing Network resources project that they had, and they let us try it into the emulator and simulator integrated with high performance computer, which is nice. So that's it. Thank you for your attention, and thank you for your work. If you got questions.
Do you have any question?
Hi. Yes, my main question is like, how does it scale with the number of variables, like the execution time and the resources needed? And also like these simulations, how many, like you said that you have a production of energy and other variables, how many per time step do you have as well? Like how many variables?
How many variables?
For each time step. Because you said, like, you showed a graph where you said, okay, so at time 0, this generator 1 activated for, I don't know, how many hours, and
yes.
How many of them do you have in your simulation? How many generators of electricity?
2. In this network, we have 2 generators only.
Okay.
Yes. The main idea is that for each binary variable that you add, it's a qubit more. Okay. So in this case, we have 3 for 2 generators, so we have 6 qubits. Okay, that for our computers, it's a little bit. Sorry, it's not that much, but it's complicated to adjust because sometimes in a different number of qubits, the time is so slow or it directly doesn't end. So, yes, we have 6 qubits here. That's why we want to try it into another network with more binary sets. Yes.
And the time? How long did it take to execute this?
Yes, the time. I didn't put it here, but it's actually a little bit slow. Of course, with resources that we have, it still has to grow a lot. And we are kind to test it in real computers to see if there's some quantum computing advantage here instead of classical computing. Classical computing solvers.
Okay, thanks.
Thank you.
Well, I'm going to, well, first of all, congrats for the presentation, of course. I think you were using the Cubo simulator. It's a simulator of quantum annealing.
Yes, yes,
okay.
it's Cubo.
So my question is going through the, as far as I have worked with it, you have to tune some hyperparameters sometimes. I wanted to ask you about how did you do it? Like, what was the methodology to choose these hyperparameters in order to perform better?
Actually, to be honest, we didn't tune anything because
Okay.
we were working on a DC approach, which we are expecting to be published in ICHT. But the main thing is that we used a mathematical expression, okay, the problem of binary linear integral programming model, sorry, and we used this to construct the Hamiltonian. But we didn't do anything. We didn't do anything. It was a cost function that we made ourselves.
Okay.
Yeah.
Thank you. Thank you.
Thank you.
Hi. I'd like to ask you whether you have nonlinear constraints in the original model, and if yes, how did you deal with this nonlinearity in Cubo model? And for the constraints, what was the penalty that you have been using to include your constraints inside the Cubo model?
Okay. Yes. Thank you for your question. And yes, I think that the first part of the question is
nonlinearity of constraints.
The what?
The nonlinearity of constraints.
The nonlinearity of constraints. Yes. Okay. The nonlinearity of constraints, it's deal with the classical computing part. Okay. The let's say quantum computing part doesn't have nonlinear constraints. We only play with some constraints, as I said before, connecting the variables of activation, the activation, and well, if it's active in this hour and in the previous hour. And also, we have another constraint that I didn't say, that at least one generator has to be active. Okay, so these are the constraints that we use in this model. Are simple, yes. And I think that you talk about the penalty. Yeah, the penalty factor is calculated using the maximum cost and the least cost, and you multiply for the maximum cost possible. So it's penalized with this range. It's a tricky thing. Talking about the hyperparameter tuning and something like that, it's a tricky thing, the penalty factor, because you have to tune it correctly, because sometimes it doesn't work at all, or it works that much that it slows the simulation, and the results are not that good. That's important part, yes. We're using this part, this automatic penalty factor, because we have a minimum and a maximum. Yes.
Okay, thanks. Thank you.
Do you have any last question?
In the algorithm, when you fail the possible solution and you run again on a quantum computing, what do you change? Do you run again just for try, or do you change the penalties, or what is the process?
No, the process is that when you don't find the optimal solution, or it's not technically possible, because sometimes if I didn't add this constraint of at least one generator has to be active, of course the cheaper one was both inactive, but this doesn't work. So if this is the solution that finds and it's not possible, is added to the build function with the penalty factor. Okay, so you have the objective function plus the a, that is the penalty factor, multiplied by these constraints. So if it finds this the solution, if you are minimizing, it will give you a huge number. So it's discarded. That's how it works. So I don't change anything, it's automatic. You just put this constraint into a penalty, and that's it.
Yeah, but you change the penalties between each interaction.
Well, yes, that's right. I add them, so yes.
Okay, and with random penalties, or with some algorithm to adjust the penalties?
No, as I said before, the penalty factor is adjusted itself with the maximum and minimum cost, because it's a function that has a minimum and a maximum.
Yeah, but
both
if
possible.
you have a non-feasible solution,
yeah,
and you run again, how the penalties are adjusted between the multiple constraints?
Well, I don't know that. I don't know about that. If you want, later we can discuss it. If you want.
No problem.
And because we don't have time. But yes. Okay. Good one.
Okay, so let's thank the speaker again.
Thank you.
Thank you.
Hablamos desde aquí y luego para preguntas de aquí, ¿vale? Y aquí tienes para pasar de diapositiva.
Okay, let's now listen to the talk by Guillermo Lujilde Fernandez, titled Quantum Algorithms for Algebraic Structures.
Okay, thank you very much for the introduction. Quantum computing can be used, surprisingly, for pure abstract algebra, and it's actually pretty useful. And we try to expand that range. It's not going to get too mathematical, I hope. So some very known example of quantum algorithm that can be used for algebra is the Shor's algorithm, basically. And there are a lot of examples of them that are polynomial in quantum computing, and they are not polynomial in classical computing. So we try to find more. Specifically, we were very interested in abelian subgroup problems because for some reason there are a lot of them that are solved in polynomial time. For example, the membership of any element of a group to a given subgroup, abelian subgroup, or even the hidden subgroup problem, which is one of the most important ones in quantum computing in general. So our first aim was to try to extend these algorithms not to, instead of subgroup problems, to ring problems. So what kind of difficulties could we find when we add a new operation, the product, to the mix? And if we are able to find some interesting results, then what doors are now opened for any other results to be solved? So the way we approached this was, if we are able to find additive generators for any subring, then we can interpret the subring as an abelian subgroup, and that's it. And you can reduce any subring problem to an abelian subgroup problem. So the solution is this. We start with a subgroup H, which is basically the abelian subgroup generated by the original generators of the subring S. So it's smaller because it doesn't have products, but it will be growing until reaching S. So since the products are probably not inside the group, we just check if the product between every generator of S and every generator of H is inside H. This membership problem is a membership problem in an abelian subgroup, so it's okay, we can solve it in polynomial time. And if any of the products doesn't belong, we just add it to the generators of H, and H grows. By Lagrange's theorem, we know that every time it grows at least to twice its size. So that ensures that we are not going to do an exponential number of operations, and finally H will reach S, and we will have additive generators for S. So once we solve this problem, almost automatically we have a lot of subring problems solved. Let me point out the membership to a subring of any given element of a ring, equality between subrings, or even finding generators for the intersection of two subrings. And now that we have a lot of new results available for rings, we can try to solve some other problems that are specific for subrings, for example, the ideality of a subring, or even checking the invertibility of an element of the ring. All of these are solved in polynomial time, quantumly, and none of them has polynomial's classical solution, at least to the best of our knowledge. I would love to detail some of them, but I don't have time. However, throughout the process of solving this, we faced a lot of problems that have to do with existence. Checking the invertibility of an element is an existence problem. You want to find the inverse. some other examples are existence of idempotent elements, or even deciding if a structure is commutative, for example. You want to find pairs that don't commute. So existence problems are very common, and in quantum computing, they can be dealt with, for example, with the Grover's algorithm. But Grover's algorithm is not for groups or rings, it's for finite sets in general. So we took a step back and we started working with magmas, which are the most general algebraic structure possible. They have one operation and no properties satisfied at all, just one operation. So anything that works for magmas works for any algebraic structure in the world. And we proposed a very interesting solution to these existence problems because it was a hybrid solution. So it's a quantum algorithm that is not better than the best known classical algorithm, but if you combine them both, then the result is better than any of those separately. So it was a very interesting solution. And it was extra interesting because it was actually hiding a very curious generalization of the Deutsch-Jozsa algorithm. That was very surprising, but it's true. The Deutsch-Jozsa algorithm is kind of an existence problem too. So that's the one I'm gonna detail now because it's very fun. This is the original one. So we have to decide if a given function is constant or balanced between these two values, 0 and 1. And the point of the solution is that we are gonna sum the result of the function to the minus state, so that if the function is 0, the minus state remains the same, but if the result is 1, then it flips sign. That's the only thing that you need in order to make the trick work. So the generalization that we faced naturally through the other solutions was this. What if the function is not a constant or balance between two values, but between two sets? Then which state should I put here in order to make the trick work again? So I need a state that when you sum an element of A, it remains the same. And when you sum an element of B, it changes sign, or vice versa, doesn't matter. The solution is understood with this basic example. Here, A only has one element and B has two. And the point is to construct this state that features the elements of A positive, the elements of B negative, or the other way around, doesn't matter, and every possible sum with a sign. For example, B1 plus B2 is positive because it features two negative elements. So the sign, it's like multiplicating signs. You can check very easily that this state remains the same if you add A1 and changes sign if you add any of these two. So it satisfies what we wanted. However, since these elements are completely arbitrary, they might satisfy things like this. If this is the case, then this state in the superposition, if you associate negative numbers to B, then it should be negative because it only has one element of B. But if you associate negative signs to the elements of A, it should be negative too because it has an odd number of elements of A. However, the state 0, which is the same state because they are equal, must always be positive here. So that's kind of a contradiction. That follows us to the next definition. We say that the sets are inconsistent if any of those equations holds. That's very easy to check. It's just a system of equations. And what we proved is that if the sets are consistent, then the previous state, that is so important, can be constructed deterministically with a quantum procedure with the same complexity than a system of equations, because that's the hardest part of the process. It's just a system of equations. If they are not consistent, then the state itself doesn't make sense, and you have to try some other solutions that are worse because they need more applications of the oracle, and they are not really a generalization of the Deutsch-Jozsa algorithm. So fine, in summary, we were able to find a nice amount of solutions to several sub-ring problems and ring problems in polynomial time, that they don't have a classical polynomial solution. And about magmas, we suggested a hybrid approach to existing problems that is quite interesting and it can be improved. And a generalization of the Deus-Jots algorithm that is not always possible, but when it is, it can be applied to some existing problems, as we saw before. So finally, I have to thank the sponsors of this work, which are the National Institute of Cybersecurity, through the project 2 of Quantum Spain, and well, there are a lot of them. My supervisors work in a lot of projects, so they have to appear there. Thank you very much for your attention, and I could ask any questions.
Thank you, Guillermo. Do we have any question?
Hey, thanks for the work. I really like it. I didn't understand, what are your results for non-commutative groups? Like, do you have efficiency for which non-commutative groups? Also,
Okay.
within commutative, have you looked into symplectic structures? These are used sometimes for membership testing.
Okay, is it fine? Okay, the commutativity and all of those problems are existence problems, or they are here. Existence problems, they are very general, so they work for magmas for any structure. And the problem with that is that you have too much generality. So finding polynomial solutions to those problems is, I think, impossible. I think it's even proof that it's impossible. So the best thing that we can do is Grover's algorithm, which is the complexity is quadratic. It's a quadratic gain with respect to the best known classical algorithm, and you can improve that. In other articles, we were able to improve that probability of error and complexity, but it will never get down of that order. And the same for the rest of the problems.
Do we have any other question? Well, if not, let us thank the speaker again.
Aquí y luego para preguntas desde este, ¿vale? Y luego para pasar diapositivas con esto. Esto para punteros láser y esto para...
Let's now listen to the talk by Marta Losada, titled Kunka, a Distributed Quantum Computing Simulation Framework.
Hello, so my name is Marta Losada, as he said. I come from CESGA, from Galicia, and I'm working on the Quantum Spain project. And at CESGA, we are developing Kunka. It's an API. It's on a distributed quantum computing simulation framework. So there's a lot of wording here. I'll go step by step. So the first concept that I want to introduce is distributed quantum computing. So as you know, as researchers, you do your simulations for calculating your stuff. And you know you can parallelize, right? In HPC environments, you can parallelize threads or using MPI also. And you can actually do this in the with quantum resources. So distributed quantum computing puts us in a place where in the future we might have access to several QPUs, right? Here I show Cumio. It's the quantum computer we have at CESGA. And let's say I have in the future access to 4 QPUs, right? So there's many things that I can do with them. So there's 3 approaches in distributed quantum computing. The first one is embarrassingly parallel distribution. So it's mainly a classical distribution of tasks. It's like you have 3 circuits and you don't want to waste time executing them sequentially. So you might want to execute them parallelly in 3 QPUs. So there's no communications needed, and it's just a classical distribution. But this brings me to the next approach, where you might need classical communications among them. So let's say you have iterative quantum phase estimation or any other algorithm that requires making an intermediate measurement in one circuit and sending a bit to another QPU in order to perform a conditioned gate or something. So this is still a classical distribution, right? Because in the classical computing, you can communicate MPI processes. So this is not new, right? But this brings me to the last approach, which is quantum communications. So let's say I have 3 QPUs of 5 qubits each, and my algorithm requires 15 qubits. So if I have 3 QPUs with good enough quantum communications, I could do a quantum distribution. This is different. We don't have a classical counterpart. And this way, the quantum state is shared between all the QPUs. So I do not have access to 3 QPUs, not even them having quantum communications. Maybe IBM people do. I don't. In Spain, it's difficult to have access for this. So what we want to do with Kunka is to have this simulated in an HPC center. You do actually have access to supercomputers. You have Finisterrae in CESGA. You have Mare Nostrum in BSc. So with Kunka, we want to be able to simulate these setups for you to run your distributed algorithms to practice for when we have access to this. So right now at the moment, we do have the inversely parallel version, and we actually just got to the point where we can have classical communications among the virtual QPUs. Remember, this is all simulated, and we are getting to quantum communications. So let's explain what is a virtual QPU. So virtual QPUs are allocated in classical resources, and they have 3 main building blocks. So a server, that is one entitled to communicate with the exterior, so it receives the circuits or quantum tasks, and then sends out the results. And then the circuits are actually simulated by the simulator, low-level simulator, accordingly to backend properties. So backend, it's number of qubits, topology, coupling map, and noise profiles, and everything else that the simulator needs in order to emulate the behavior of a real QPU. So as a user, how do I set up these virtual QPUs, and how do I interact with them? Okay, so for setting up, you would go to your terminal in your HPC environment, Finisterrae or Mare Nostrum, and you have a command QRaise to raise the QPUs. Pretty simple. You just tell them, specify the number of QPUs you want to deploy and the number of for how long. You can have them with classical communications, quantum communications. You can provide calibration data from real QPUs in order to simulate them. Then to finish using them, you just drop them, because in HPC centers, resources are really demanding, so we don't want them to stay there for hours. So you just use qdrop, and then we also have qinfo to know what things you have deployed. And this is really nice. So let's say I have deployed my QPUs, and I have 3 QPUs waiting for me to interact with them. How do I do it? With a Python API. So this Python API instantiates a client associated to each QPU. And as I said, it communicates with the server. So this client sends the circuits, the server receives the circuits, tells the simulator to execute them, and when it's finished, when the client asks, the server sends out the result. So this is done by a library, Python library. You just import the needed functions to interact with it. So let's see an example. You would just have your Python program in Qiskit or so on. You can have your quantum circuit programmed with Qiskit or even with Kunka circuit. And you would import get QPUs and gather functions that we will see what they do. So once I have deployed my QPUs, right? So I use the get QPUs function, and a list of my QPUs is returned. So a list of Kunka objects, like Kunka.QPU objects that are associated with these QPUs that I have deployed. So what I can do is do a for loop and send each QPU a circuit. It's just QPU.run. And this way, what I'm doing in each iteration of the for loop is the client of that QPU sending to the corresponding server a circuit. But this is only sending. I'm not waiting for it to finish. So this for loop is actually asynchronous. There are not blocking calls. So here you see the parallelization. But then when I ask for the results, when I tell Kunka to gather the results from the jobs that I send, what I'm doing is I'm telling the client to call for the results. But when I call for the first one, here I have to wait for it to finish. So this is the blocking call, but while I wait, everything is executing. So here's the parallelization. And finally, you can just print your results async Qiskit. It's really similar. This is the most basic parallelization that you can do with the API. I actually have a use case for my master thesis, which is the distribution of the variational quantum eigensolver. And I simulated 3 IBM machines together with Cumio, the quantum computer in Thesga. And I actually got really nice results. You can check out my poster tomorrow if you have further questions. So here's my team. We at Thesga, Dani, me, Jorge, and Álvaro. We are located at Santiago de Compostela. And that's basically everything. Here's our GitHub. If you're interested on using Kunka, right now it's only available in Thesga resources, but we are looking for implementing it on other supercomputing centers. So that's everything.
Thank you, Marta. Do we have any questions?
Hi, thank you very much for your presentation. Towards the end there, well, and you mentioned that you would explain it in your poster, but I believe you said you had like a use case where you'd actually applied this library, right? With 4 quantum computers, was it? So I understand that you were using like classical communications there, or was it just an embarrassingly parallel task?
It was actually embarrassingly parallel.
Okay.
It was just a shots distribution. There's also many things that you can do, but for the BQE, it's just what I did.
Okay, thank you.
Yeah.
Do we have any other question?
Hi, thank you so much for the presentation. It was very interesting. And I was wondering if the case why this third use case where the communication is quantum is yet to be developed because you need kind of a quantum memory to store this information and be sent and received.
Yeah, you're right. So we are developing actually, but what you have like the bottleneck when you have quantum communications is that you cannot actually have different simulators. Like in classical communications, you can, because you can communicate, like this is also everything classical, right? Low level. So you cannot communicate, in classical communications, you can have several processes, but when we have quantum communications, we are required to have one main process. We are trying to see how can we have many processes, and when they communicate, we have big, like they join together in a bigger one. We are still getting there, but yeah, that's mainly a bottleneck with the memory also. But we have many resources, so I think, limited, of course, is not infinite, but yeah, I don't know if this answers the question.
Yeah, thank you.
Hi, thank you very much for the presentation. It was very nice. I wanted to ask whether you have to take into consideration when you're setting up the containers and doing the simulation or the thing it does, whether you have to take inform it of how many iterations are you going to do in order for it to communicate to the other simulations.
Can you repeat the question?
When you're doing the just parallel one, I guess you're
You're talking about embarrassingly parallel?
Yes. Yeah, like
Okay.
In that case, you're just calling and
Yeah.
creating them by themselves. But when you're running them and they're supposed to be communicating, like the other cases,
yeah,
you have to take into consideration any other thing, because if you're doing a loop and you don't like how do you say, those environments don't know with how many other environments they have to communicate, is that a factor that has to be taken into account, or?
So if you're talking about the Python loop I showed, or?
Yes, or like the relation that they have, those environments have between themselves. Is it something that has to be taken into account, or is?
Yeah, actually, when you deploy the QPUs, you have to insert the flag of classical communications. So that requires to have a special scheduling of the instructions when they're executing. So when you start sending the circuits, you have to know, like you already know that you're gonna be communicating, like there's information in the circuits about who is communicating with who, so everything is scheduled low level.
Okay, thank you very much.
Any last question? Okay, then let's thank the speaker again.
Por aquí y esto para preguntas, ¿vale? Y luego para pasar diapositivas, este mando y este para puntero láser, ¿vale?
Okay,
Let's now listen to the talk by Pablo Viñas Martinez, titled Context-Aware Gate-Set Tomography, Improving the Self-Consistent Characterization of Trapped Ion Universal Gate Sets by Leveraging Non-Markovianity.
Thank you. So thanks, everyone. I'll try to be a bit fast because I think we're a bit late. But yeah, I'm Pablo Viñas. I'm a PhD student at IFT. And I'm here to present our latest work, which I did in collaboration with my thesis supervisor, Alejandro, to whom I would like to thank, first of all. I would also like to thank the organizers for giving me the opportunity to present my work here again this year. So as a summary of what I'm going to talk about, I will give a very brief review about what GST is, and then I will just present a couple of issues that this protocol has, and I will explain how do we address and try to solve those challenges, okay? So let me start by saying something rather obvious. Imagine you are coming to this workshop in the conference by car, and then suddenly your vehicle breaks down. Then probably you will agree with me on the fact that the first logical step to fix your vehicle is trying to guess what happened, okay? Trying to randomly replace, for example, a wheel won't work, probably. So that's essentially, to some extent, what quantum tomography is about. So what you typically want here is to infer information about what's going on in your quantum processor, and more specifically about what is not going on as well as you would expect, okay? In a more technical way, what you do in gate-set tomography is first, you define a set of operations that you have available in your processor, plus an initial reference state and a POVM to perform measurements. And then you very carefully design some sets of circuits whose outputs you are going to collect from the lab, and then you are going to try to fit those results to a theoretical model which you use to describe your processor. And in that way, you recover a mathematical representation of the gates that your processor uses, okay? Now, don't get me wrong, this protocol is quite challenging. It has several issues that you have to carefully care about, but the basic idea is essentially what I explained. Okay. If you are curious about this, you have a couple of references here. But yeah, that's the main idea. Now, apart from these technical issues that more or less can be overcome, there are two main challenges, two main issues which really limit the performance of GST. So on one hand, the most apparent one is the fact that the number of experiments that you need in order to perform this fitting is really large. To the point that even for 2-qubit gate sets, this is not practical. Okay, so that's really a problem to perform GST. Now, the second one, it's also very fundamental. It is related to the fact that GST does not capture context-dependent dynamics. Now, let me explain what this is with an example which I think illustrates it very well, which is this long sequence gate set tomography protocol. So this long sequence GST, it's a improvement with respect to this original GST protocol in which you basically repeat certain combinations of gates many times in order to amplify errors, okay? And once you have amplified those errors, you can recover them with this fitting at a enhanced accuracy. That's the idea, okay? Now, the problem with this is that inherently it assumes that the gates that you're applying act in the same way at any point in your circuit. And this is not always the case. In fact, when you go to certain precisions, what you realize is that, for example, non-Markovian dynamics can induce some effects which change the way in which the gate acts from one point to the other point. And therefore, this is like if you had, for example, a system of coupled pendulums and you were expecting the whole system to behave as a read-it system, but as soon as you deviate a little bit from the initial conditions that you expect, you have something completely chaotic. And you cannot predict what's going to happen. This is roughly the same thing, okay? So how do we address these issues? Well, the first one, I already talked about this last year in the same conference. You have the work available in this QR code. But what we do essentially is using physically modeled parameterization for that gates in order to reduce the number of parameters that we need to characterize, okay? In particular, in that work, we used single qubit gates only. And what we did was modeling qubits as two-level systems in which frequencies can have stochastic fluctuations. And then you have a driving agent which can also suffer from these kind of fluctuations, both in frequency and phase, okay? And that, which already describes many, for example, trapped ion processor devices, leads to a substantial decrease in the number of parameters that you have to characterize. And therefore, it also leads to a substantial decrease in the number of circuits that you need to execute in the lab to get a target accuracy, okay? But the point is, okay, this was great, but it was only valid for single qubit gates. And if you want to perform powerful quantum computation, of course, you need entangling gates, okay? So our question was, can we extend this formalism so that we can model 2-qubit gates, at least for these trapped ion devices, so that we can perform useful gate set tomography? And the answer seemed to be yes. In particular, we are trying to model these light shift gate interactions that you can find in trapped ion devices. Those are interactions in which you have spin-dependent forces, and the way you engineer those forces are basically by some Hamiltonian in which the phononic degrees of freedom undergo trajectories in phase space, okay? Now, when those trajectories are completely closed, you don't have any kind of entanglement between phonons and ions, but the total spin states acquire some phases which are proportional to the area enclosed by those trajectories, and that's more or less how you produce entanglement. This is the ideal gate dynamics, but of course we are modeling noisy gates, so we needed to model also these errors I mentioned. So on one hand, we also modeled frequency fluctuations, as I previously told, because you can have, for instance, magnetic noise in your qubits, which lead to this kind of noise. But the important thing here is the following. I told you that this works by closing trajectories in phase space, but the thing is that if you select a specific time for your gate, you can only close trajectories for one motional mode of the ions. So for example, you can close trajectories for the center of mass, but you cannot close the trajectory for the breathing mode in which ions oscillate out of phase. Okay? And that leads to residual entanglement and to a noise which is thermal. And that's why it is proportional to this mean number of phonons in the mode which you are not being able to close. Okay? But if you are able to derive a quantum map including those two main sources of errors, then you can do essentially the same thing as what we did with single qubit gates. And that's exactly what I show here. The figure is pretty similar to the first one I showed, and everything seemed to work fine until we realized something, and I panicked for a couple of days, which was basically that, you know, to derive this effective spin map for the light-shift gate, we assumed at some point that the initial state between ions and phonons was separable. Now, that's true for the first time you apply the gate, but once you have applied that gate, you have some residual entanglement. So you cannot assume that again. And therefore, the quantum map that we derived was not consistent with this long sequence protocol I mentioned before. Moreover, because this light shift map now depends on the amount of entanglement with the phonons, now you have a gate which entirely depends on an external variable. And therefore you have completely context-dependent dynamics, which is not compatible, as I mentioned, with long sequence GST. So this was like a big issue, okay? And therefore, what I asked myself was, okay, can I still get an effective map for the spin channel which comprises the whole sequence of LS gates, considering also those context-dependent dynamics? And the answer is yes, you can. And in fact, the only difference with respect to the first map is that now the thermal error does not amplify linearly. It is periodic. And that periodicity, you can see it here. Let me explain why this happens. So essentially, first time you are not able to close a trajectory in phase space, you have some residual entanglement and also some residual displacement. Now, second time, it happens again, and it begins to accumulate as you repeat the gate. And what you realize is, after you have applied the gate many times, the trajectory in phase space undergoes precession, and eventually it comes again to the origin. That's why you see this periodicity. But the important thing here is that, as you can see, for the first part of that amplification, you have superlinear scaling compared to the linear scaling that you would be expecting for long sequence GST. And what that means is that, at least theoretically, you could perform GST with precisions which are not inverse linear in depth, which is what you expect from traditional gate tomography, but rather to precisions which go as 1 over depth squared, which is a big improvement. Now, this was the predictions that we made using Fisher information, and the question was, is this really the case? Can we obtain these results? And it turned out to be the case. We simulated gate tomography, and in fact, we obtained estimations for the thermal parameter which scales as 1 over p squared, which is the main take-home message in this presentation. So yeah, the basic conclusion is that context dependence can be used to enhance precision in gate set tomography. And that was basically all. So I conclude with some future directions with which I used last year, which are basically the same, except for the fact that second one is already explained. So yeah, that was all. Thank you very much.
Thank you, Pablo. Do we have any question? If not, I had a really quick question. In the previous slide, you showed that the error showed some spikes. Can you explain, maybe you already explained it, but I maybe didn't follow, why those spikes happen?
Yeah, that's a really good question. I did not explain because I did not have much time. So those spikes are precisely the points in which the trajectories close in phase space after many applications of the LS gate. So what happens is that essentially in that point you don't have any sensitivity to the thermal error and you cannot recover that parameter. But the good thing is that if you tune the trap parameters in your trapped ion device, you can displace that peaks, that region, to the right as much as you want. Sorry. So it is not really a problem. But I saw it here to, for consistency with the results.
So in principle, you can keep the p-squared asymptotic behavior as long as you want.
In principle, you can, and also you have to take into account that for the 1/p behavior that standard long sequence EST exhibits, you cannot keep either that 1/p behavior forever, because at some point you have a noise to signal ratio which is too big and you don't get any information. So that's not a real problem. Yep.
Okay, thank you. So let's thank the speaker again. And now we go to lunch. As I said before, there are two canteens. You can go to the one here in the campus, or you can follow us to the other one. Thank you.